On June 21, 1919, the fleet-wide scuttling order passed down by Rear Admiral Ludwig von Reuter echoed through the steel corridors of the interned German battlecruiser Hindenburg, initiating a calculated and irreversible sequence. Sea valves were opened wide. Across the interned fleet, engineers broke open vulnerable intake points and seawater pathways with whatever heavy tools were at hand. This multi-point scuttling ensured the immediate, simultaneous flooding of the engineering spaces, coal bunkers, and lower magazines. It was a perfectly executed industrial assassination of a massive naval asset. The ship took on thousands of tons of seawater in a matter of minutes. The loss of buoyancy was absolute, engineered specifically to be unrecoverable by standard towing vessels. Sitting at anchor in Scapa Flow in the Orkney Islands, she was one of the most conspicuous giants of the defeated fleet. When she finally went under late that afternoon, it marked one of the final operational movements of a massive strategic suicide. The Hindenburg settled into the glacial mud and immediately became the ultimate prize and the ultimate obstacle for any future clearing operations in the British anchorage. She was a warship of terrifying scale, roughly 690 feet long, a true leviathan of early 20th century naval engineering. Her design displacement sat at about 26,000 tons, hardened armor plate, heavy internal bulkheads, and massive artillery turrets. When the scuttling order took hold, the flooding played out with deliberate symmetry, taking her down without the violent roll and capsize that claimed so many sister ships. The Hindenburg is widely reported to have sunk upright on an even keel, dropping through the water column to the seabed in about 70 feet of cold, dark water. Because the water here was shallow and the hull was so immense, she did not disappear completely beneath the waves. Her vast command superstructure, heavy tripod mast, and massive exhaust funnels remained visibly protruding high above the surface of the sea. To an observer on a passing boat, she looked like an active warship navigating through a low fog, but her main deck and all her lethal machinery lay submerged under millions of gallons of salt water. This rigidly upright posture presented a unique and highly deceptive trap for the salvage syndicates attempting to reclaim her. An upside-down hull offers a continuous solid steel basin that can sometimes be pumped full of compressed air to generate massive buoyant lift. An upright warship provides no such clean pneumatic envelope. The upper decks of a battlecruiser are heavily riddled with cargo hatches, ventilation shafts, ash ejectors, skylights, and complex companionways. Every single opening provides a free, unrestricted path for the ocean to enter and escape. The post-war industrial salvage imperative dictated that the vast quantities of high-grade military steel resting in Scapa Flow had to be aggressively recovered to feed the hungry commercial furnaces of peacetime Britain. The towering Hindenburg was the undisputed crown jewel of this sprawling underwater scrapyard. To simply leave her rotting on the bottom was to forfeit a massive fortune in premium scrap metal, while simultaneously leaving a severe navigational hazard right in the heart of a vital deep water fleet anchorage. The commercial rights to the wreck were eventually secured by private enterprise, setting the stage for what would become one of the most mechanically complex physical challenges ever attempted in maritime history. Standard heavy cranes and mechanical lifting barges were completely and utterly useless against an object of this profound magnitude. There was no surface vessel in existence capable of dropping heavy wire ropes under a fully flooded armored hull and hoisting it dead weight against the immense grip of seabed suction. Furthermore, as the sheer mass of the static water trapped inside her cavernous compartments added tens of thousands of tons to her already crushing dead weight. The unyielding physical reality of the situation left the engineers with only one possible mechanical path for recovery. The salvage teams would have to turn the sunken deadweight ship into its own massive lifting pontoon. They would have to aggressively expel the internal water from inside the hull faster than the surrounding ocean could push it back in. To achieve this massive displacement of internal water, the engineering directors faced a brutal geometric reality. They were staring down at a cavernous steel vault resting entirely on the seafloor. It was heavily armored, incredibly massive, and completely saturated with the ocean. Before a single high-capacity steam pump could be engaged, they had to somehow render the submerged, shattered wreck completely watertight from the outside in. The upright geometry of the battlecruiser created an immediate and brutal physical trap for the salvage syndicates. That upright posture turned the ship's own access points into liabilities the moment salvage began. Only after the upper decks were sealed off from the sea could the first water be pulled from inside. This was not a localized combat breach caused by a single torpedo strike. This was the deliberate, engineered porosity of a fully functional military vessel. To make that steel hull hold air and lift like a pontoon, they had to fight the ship's own design at every seam. The salvage teams initiated a staggering campaign of underwater sealing. Working by hand in near-freezing water, the heavy commercial divers mapped the immense acreage of the sunken decks. They cataloged over 800 individual hull openings that had to be physically blocked before any lifting force could be applied. These were not uniform penetrations. They included vast armored ventilation gratings, narrow glass portholes, massive cargo hatches, and intricate stairwells originally designed to move thousands of enlisted crew members. Over several grueling months, the diving teams manually fabricated and installed custom barriers over every single breach. They bolted and braced timber and steel shutters into place, then packed and sealed seams with heavy compounds like tallow and cement to choke off the sea's countless paths into the ship. Each custom patch had to be meticulously constructed to withstand the immense hydrostatic pressure that would bear down upon it from the outside ocean once the internal water levels began to drop. If even a fraction of those seals failed, the sea would immediately breach the barriers and reclaim the newly emptied space. Sealing the colossal steel vault was only the first half of the thermodynamic equation. To forcefully rip millions of gallons of water out of the fortified structure required a staggering application of continuous industrial power. The salvage operation deployed a massive array of heavy steam-driven pumps and air compressors mounted on surface support vessels and piped directly into the sealed compartments of the battlecruiser. These mechanical engines were voracious consumers of fuel, demanding an uninterrupted supply of raw coal to keep boilers roaring, pumps running, and compressed air forcing seawater out while holding the ocean back. But as the work gathered momentum in 1926, a massive national labor strike in May shook the British coal industry and sent fuel logistics into chaos. With coal scarce and unreliable just as the operation prepared for its most power-hungry phases, the supply chain threatened to starve the boilers, stall the machinery, and flood hard-won progress. The engineering directors hit a fatal bottleneck. The ship was sealed, the pumps were ready, and the boilers that powered everything were about to go cold. With mainland coal locked up by the strike, they turned to the graveyard around them. Nearby, the sunken battlecruiser Seydlitz lay partly exposed, her coal bunker still holding usable fuel left from the end of the war. The salvage teams deliberately shifted their heavy equipment over to the neighboring wreck. Using mechanical tools, they cut into accessible sections of the dead ship to reach what fuel they could. In a desperate act of improvised extraction, workers hauled coal out of a sunken warship simply to feed the steam boilers required to raise another. It broke the strike's grip, just enough to keep the operation alive. It kept the fires burning and the heavy machinery running when the mainland supply failed. With an uninterrupted fuel supply forcefully extracted from the surrounding nautical graveyard, the massive expulsion of seawater finally accelerated. The relentless mechanical draw of the steam engines began to pull the ocean out of the sealed compartments, forcefully lowering the internal waterline foot by foot. But removing thousands of tons of static mass from inside a towering, upright steel structure sitting loosely on an uneven seafloor is not merely a problem of continuous suction. It actively alters the fundamental physical balance of the vessel. As heavy seawater was stripped away and replaced by buoyant air, the ship's balance began to change, quietly, dangerously, and out of sight. The human eye is useless inside the flooded, pitch-black bowels of a warship resting on the seabed. As the surface pumps prepared to pull water from the main compartments, the engineers faced a hazard hidden in the internal maze. Drain one space too far, too fast, and you create a brutal pressure gradient. The surrounding ocean and the water still trapped in adjacent rooms compress inward against exposed bulkheads that were designed for localized battle damage, not the one-sided crush of a dry void. If an internal wall ruptured, the ship would flood in an instant, erasing progress and twisting her structural spine. So the plan demanded more than pumps alone. They needed a way to get men and timber into newly created air pockets, shore up what mattered, and keep the interior from collapsing as the waterline dropped. To bridge the gap between the surface and the deep interior, the salvage syndicate engineered a brilliant and brutal mechanical bypass, deploying pressurized access through airlocks. They positioned rigid steel access trunks over openings in the upper deck and sealed them hard against the plating. Above the surface, but each trunk was capped with a heavy airlock chamber. High-capacity compressors then drove compressed air down into the compartments below, displacing seawater and carving out temporary dry working spaces inside the wreck. Once the air held, the route was no longer through water, it was straight down steel. Men climbed down the long, dark vertical boiler tubes, passing through the pressurized airlock chambers, and descended straight into the belly of the warship. They stepped out onto the damp steel floor plates miles away from natural light, working entirely in an artificial atmosphere. Breathing the heavy, compressed air, the construction crews used standard heavy tools to aggressively wedge massive timber shores against the towering steel bulkheads, physically locking the interior walls into rigid alignment. They worked continuously in the eerie, pressurized echo chambers of the dead ship, building the critical internal skeleton required to survive the impending mechanical lift. When the internal bracing was finally locked into place and inspected, the men evacuated the pressurized tubes and the main surface pumps were cleared for massive, uninterrupted extraction. The tremendous suction began to rip thousands of tons of static water weight out of the reinforced compartments, rapidly increasing the overall buoyancy of the towering steel vault. As the engineered vacuum forcefully altered the ratio of air to seawater inside the hull, the immense physical weight pressing the ship into the mud began to steadily decrease. But removing that massive internal anchor actively changed the geometric balance of the vessel, fundamentally destabilizing her footing on the hard, uneven sea floor and initiating a lethal physical reaction. By the time the campaign was finally finished, the price tag would climb to roughly 30,000 pounds sterling, an immense commercial fortune in 1926. And in a single bad turn of sea and weather, months of meticulous engineering could be wiped back towards zero. The massive steam engines had been running at absolute maximum capacity, drawing thousands of tons of dead seawater out of the sealed upper decks of the sunken battlecruiser. For the first time in 7 years, the towering steel structure began to feel the immense upward pull of artificial buoyancy. The sheer lifting force generated by the empty compartments started to fight against the crushing grip of the deep seabed mud. But as the internal water levels steadily dropped, the salvage crews unknowingly unlocked a terrifying and highly lethal physical mechanism hidden deep inside the cavernous hull. Pumping a massive flooded compartment dry is not an instantaneous process. As the powerful surface pumps extract the sea, the waterline inside the ship lowers, creating vast, shallow pools of trapped liquid stretching entirely across the enormous internal width of the warship. This introduces a catastrophic hazard known as dynamic water shifting. Unlike solid steel engines or heavy armor plates that press straight down through the center line of the vessel, liquid water is entirely unbound. If the ship rolls even a fraction of a degree, thousands of tons of this internal water immediately surge toward the lower side. This massive, unrestrained shifting of weight actively destroys the fundamental center of gravity. The heavy fluid aggressively amplifies the lean, creating a self-feeding, uncontrollable pendulum effect that threatens to violently and rapidly capsize the rising hull before the pumps can remove the danger. This lethal internal fluid dynamic collided with a hidden, external geometric trap. As the immense buoyancy increased, the hull strained to lift, but the heavy steel bottom was not resting on a flat, uniform plane. The stern was effectively perched on a narrow, rocky contact, a brutal fulcrum only about 3 feet wide. As sections of the ship began to break suction and pivot, the vessel teetered on that jagged stone edge and developed a dangerous list. To restrain it, the engineers rigged thick, 9-inch heavy steel wire hawsers and lashing the rising hull to supporting vessels. Then the anchorage delivered the blow that ended the attempt. On August 24, 1926, a gale hammered Scapa Flow. Heavy seas slammed into the exposed structure and punished the support craft. Under the compounded strain, the 9-inch stabilizing hawsers snapped and control collapsed. With the list worsening and the risk of a full capsize rising, the operation was aborted and the wreck was deliberately reflooded to settle back into the mud. The wreck was deliberately reflooded and settled back into the mud, a costly failure that left her footing compromised and proved that raw vertical pumping by itself would not beat the anchorage. Instead of blindly attaching more massive steam pumps to fight the uncontrollable roll, the salvage directors made a violent pivot in their engineering logic. They realized that simply overpowering the ocean with raw suction would never solve the fundamental geometric instability of the towering sunken wreck. The massive battlecruiser was too top-heavy for a clean vertical lift. Every ton high above the keel magnified any slight lean into a catastrophic capsize, so they executed a brutal mass shift. Cutting crews descended upon the exposed structure with torches and rigging. They systematically removed the superstructure, the heavy tripod mast, and the forward main gun assembly, ripping weight from the highest points to drive the center of gravity down. This structural amputation transformed the towering hull into a flatter, more stable barge. But lowering the center of mass was only half the equation. The stern still teetered on uneven ground. Since the engineers could not excavate solid rock from beneath 26,000 tons of deadweight, they altered the seabed geometry instead. They fashioned a massive concrete wedge using a cut-out section of a scrapped German destroyer's lower hull, then filled it with 600 tons of dense industrial concrete to create a monolithic support shaped to the problem. Once dragged and forced into position beneath the stern and reinforced with additional supports as needed, the battlecruiser's footprint was widened and its posture locked against the seabed. With the upper mass amputated and the stern braced by custom concrete, the engineering teams finally ordered the heavy steam valves opened. The massive mechanical pumps were fired up for the ultimate deciding test against the crushing ocean. On June 21, 1930, the next operational window opened over the anchorage. The heavy surface fleet ignited their boilers, channeling continuous steam pressure into the pumps and compressors tied to the amputated battlecruiser. The machines roared and the sea was driven back. But even then, the physics of that anchorage did not forgive. The hull began to list, control slipped, and the ship sank back again. Weeks later, in late July 1930, they came back for the deciding test. The boilers were lit again and the steam valves were opened. But this time the ship itself had been changed. With the top weight cut away and the stern braced, the previously lethal dynamics were finally contained. As internal water levels dropped, buoyancy overpowered the grip of the mud. Suction broke. The ruined battlecruiser began a slow, hard-won ascent through the dark water column. There was no sudden, uncontrollable surge to the surface. The engineers throttled the machinery, managing internal pressure and residual liquid weight to hold a usable keel. The hull listed slightly, then steadied as the lift settled into balance. Foot by foot, the flattened upper decks rose through the cold ocean. As pressure eased on the patched skin of the hull, the seals held, and the lift kept coming. The amputated main deck finally breached the surface of the sea. Millions of gallons of ocean cascaded off the thick armor plating as the colossal steel barge exposed itself to open air. The pumping crews climbed onto the slippery, rusted decks, carrying hoses to drain the remaining flooded pockets hidden deep inside the lower magazines and boiler rooms. The transition from a static, sunken, deadweight trap back into a floating, buoyant vessel was a triumph of extreme physical logic. The massive warship was finally free from the seabed, floating on her own hollow displacement. With the battlecruiser fully afloat and stabilized, the final phase of the commercial salvage operation commenced. The engineering fleet surrounded the flat, decapitated hull and attached thick towing hawsers to her forward plating. This was not a standard transit. She had no propulsion, no steering, and compromised hydrodynamic efficiency. Her submerged hull was encrusted with years of marine growth, building immense drag against currents. A convoy of high-powered tugboats had to generate sustained mechanical force simply to overcome the inertia of a 26,000-ton steel island. The towing convoy worked southward down the rugged coastline. The destination was the ship-breaking infrastructure at Rosyth. On August 13, 1930, the convoy finally hauled the hulk south for the breakers, the last passage of a giant that had once dominated the anchorage. Upon arrival, the mutilated battlecruiser was maneuvered into a dry dock and secured against the retaining walls. Gates closed. The basin was pumped away for the last time. Cutting crews swarmed the exposed hull. Over the following months, industrial furnaces consumed the recovered armor plate. Bulkheads, turbine shafts, and external plating were sliced apart, hoisted away by cranes, and melted down into raw ingots. The looming hazard that had once filled the northern anchorage was systematically deleted from existence. The relentless application of engineering logic, brutal structural amputation, and absolute commercial persistence resulted in the total physical eradication of the former German battlecruiser.